Hi everybody, welcome to the next lecture on video coding, today about improved interpolation. We saw interpolation plays an important role for motion compensation with improved fractional pixel accuracy. The more precise interpolated we get, the smaller our prediction residual becomes and the more compression we get. How do we get improved and practical interpolation? In computer graphics, we have an analog problem of interpolating samples, but there it is samples given by a model or a designer instead of the pixel grid of our image. Hence, it makes sense to take a look at the approaches in computer graphics. So here you can see the example here in 2D. So the crosses are the samples which are given. So either by designer or in our case these would be the pixel samples, and each cross would then determine, say, the brightness of this pixel. And then the dashed line would be the interpolated curve with various desired properties, which is usually it should be smooth and ideally it should go through the original samples, and you can see here it's not the case. And then this curve here can be used for obtaining high resolution images using this interpolation. Yeah, so this has a parallel to the Nyquist sampling theorem for reconstruction. We have the interpolation of samples, and this tells us how to do the interpolation. In Nyquist, we do this interpolation using an ideal low-pass filter. So we know that an ideal low-pass filter basically has the sinc function as an impulse response. And this ideal low-pass filter has a upper cutoff frequency which is half the sampling rate. Right? This is what Nyquist says, and if we do upsampling, then this corresponds to half the old sampling rate. So the samples are our control points and the samples in the above picture. So Nyquist reconstruction or interpolation means our samples corresponds to our control points with the zeros in between, right? The zeros for the upsampling. The result of the low-pass filtering is then our interpolation. So this is what you can see here. Here we have points, for instance in time, but it could also be positions of our pixels. Here the crosses are our pixel values. Vertically is the brightness value, for instance, and then the dashed line is the interpolation. So that's the principle. So Nyquist reconstruction assures that there are no frequency components above the Nyquist frequency, and hence we have a minimum frequency of change, a maximally smooth interpolated curve. So this is done using the sinc function, which you can see here. So it's sine of pi t divided by pi t, and that's the impulse response of our ideal low-pass filter as interpolation function. So here you can see this function. Here I plotted the values from -4 to +4. And you can see the sinc function has this interesting property that it goes through 0 at all integer x values except for x value 0. Right? And in between you have this sinc curve going up and down, positive and negative. And now for the interpolation, you can imagine this point 0 is on the position of each pixel, and then each pixel gets such a function in its place, and then we sum them all up, and that's basically what the convolution is doing. So we assume that our samples are on the integer sample points. The interpolation function of the other samples have a 0 there, hence the interpolated curve has no influence of the other samples there, and the curve will go through the sample values. And that's also a convenient property that it doesn't change the original samples. The original sampling points are maintained after the interpolation, which is what we want. This can be seen in the following. In continuous space or time, we can write our sequence of samples as a sequence of Dirac pulses multiplied by the sample values. So this is what we can see here. So here we can see the sum going from 0 to infinity, and here we have shifted Dirac pulses, delta of t minus n. So this is centered on each n of this sum, and then it gets the value of the pixel x of n at this position n. So filtering is then a convolution of our samples with a sinc function. Continuous time convolution is, for instance, with a of t as our sample sequence and b of t our ideal low-pass filter impulse response, defined as this. So first we have our sequence of pulses. So we represent our image as a sequence of pulses where the magnitude of each pulse is given by the sample brightness, for instance, or the sample value in general. And then we take it and filter it, and this filtering is convolution, which we can see here. So since this equation and this sum is in the continuous time domain for convenience, because we don't specify how much upsampling we do, this is the convolution in continuous time. Right? You can see here we have the integration over n. So n here is now our other variable for this integration. So here it's a continuous variable, and here it goes up and here it goes down, and that's our convolution. And now when we look at this integral here, we see that the first part is our sequence of Diracs, right? So this could be our A. And then the second part, the B, is now our sinc function. So we take our Dirac sequence of our image, convolve it with the sinc function, with the ideal low-pass filter. And then we can see here that we have a bunch of Diracs convolved with the sinc function. And we know that a shifted Dirac convolved with a sinc function is simply a shifted sinc function. Right, so here we have a shifted Dirac. Right, so the area is 1, and then since it's shifted, the convolution with this is simply the shifted sinc function. So in the end, we just have a sum of x of n times sinc of t minus n. So here we have our samples, and then we convolve it, and we have those shifted versions. So here you can see it again. We have a shifted Dirac times convolved with a sinc, and that's the shifted sinc. So here now the sinc is centered over n instead of 0. And hence we get this sum here. We have a sum over the x of n times sinc of t minus n. So basically we replace the sample Diracs by the sinc functions, and then we add them all up. And here you can see an example how this works. So here we have a sequence starting at 0 in this example, and the original sample points are the red circles here. Right. And each red circle gets its own sinc function in a different color. So here you can see the first one, which has this kind of violet color. Then the next one here is this red sinc function, where you can see it's centered around 1, x value 1, and has the value of the original pixel. And here the same for the next. Here we have a green sinc function for the sample point. And here we have this kind of reddish sinc function for the sample point. And the last one here at x value 4 has this blue sinc function. You can see here just 1/2, the rest would continue here. And then the sum of all those sinc functions is then this black line, which you can see here. And you can see this black line is nice, smooth, and it goes directly through all the sampling points, right, starting here. So you can see that the black line is actually quite a nice smooth interpolation of all those points. It's actually quite a good interpolation in this way. So the sinc function is an infinite polynomial, hence it is infinitely continuously differential. So remember, the sine function is an infinite polynomial, so the same is true for the sinc function, which means we have this infinite differentiability. And this is actually better than, for instance, the so-called cubic splines, which we know from computer graphics. So this is what they use in computer graphics. And they are continuously differentiable only until the second derivative. So it's quite a lot lower, but it turns out it's good enough for computer graphics. And the thinking is, if it's good enough for computer graphics, then it should also be good enough for video, right? So why take something complicated as the sinc function if we can do it simpler? Yeah, so the problem here is the sinc function is infinitely long, right? It starts at minus infinity and goes up to plus infinity. So that's not so practical. An alternative option for the interpolation filter is a convolution of our samples with a so-called box function as a basis function. And this is really short, right? So this is kind of the opposite extreme. Instead of going from minus infinity to plus infinity, this just goes from 0 to 1 and is 0 outside this interval. But when we try to use this filter here as an interpolation filter, then this is the result, right? It's actually a piecewise constant function. So this should be the result. So you can see basically the same principle. We have our pixel values as the crosses, and then we replace each pixel value by this impulse response function. And since this is just this box, we get this piecewise constant function, which means we have jumps here from one pixel to the next. So it's not continuous. The function itself is not continuous, and that's bad because we would get artificial contours in the image. So we have no continuity. That's a problem because we have mostly smooth intensity gradients in images. Another way to preserve the continuity is linear interpolation. And we obtain linear interpolation as a basis function if we convolve the box function with itself. Right. So here we can see it. So we have two box functions, we convolve them, and then we get this triangular function here. And this goes over two intervals. It starts at 0 and goes up to 2, right? Because of the convolution here. And you can also see it has no sudden jump in the beginning and end. It linearly goes up and linearly goes down. And when we look at those two intervals, you can write each of those curves as a polynomial of a helper variable u. So this u goes from 0 to 1 on each interval. So here it goes from 0 to 1, and on the upper interval it also goes from 0 to 1. And each is a polynomial which makes us this linear function. First goes up and then goes down. Yeah, so that means we have those two intervals, and we can define a polynomial function qi of u over each interval with a local helper variable u, which is between 0 and 1. So here this I is 1 and 2. So now we have an interpolation with these basis functions. So here you can see again we have our pixels as crosses. Here's our x-axis, for instance, along a line. Could also be time, t. And here we can see the integer x values, 0, 1, 2, 3. And we have this helper variable always going between 0 and 1 within each interval. Yeah, So after the convolution, we obtain an increasing and a decreasing part for each to be interpolated interval, as can be seen in the above picture. So each pixel again is replaced by this impulse response, which here happens to be this triangular. Yeah, so each interval between two sampling points contains now two functions, the rising and the falling slope of our basis function. So when you look at this first interval, we have the falling part from the blue one and then this rising part from the red one. So each interval has two functions. We can now write this basis function as two linear functions or polynomials of first order of this local variable u, right, which varies between 0 and 1 in this interval between two neighboring sample points. So should be there. For the rising part, we get q1 of u equals u, so this just goes up. For the falling part, we get 1 minus u, so this goes down. Let the sample value at the lower end of the interval be f0 and at the upper end be f1. Then we can linearly interpolate the in-between value point as u as f of u, so this is the interpolated value. And now we have the sum of the two contributions from the two basis functions, right? So this is now the contribution of the basis function for the function value on the lower end of this interval, f0 times q2 of u. And here we have the contribution of the sample at the upper end of the interval. And for this upper end, we have the rising part, the q1 of u, right? So going back here, so here this is our q1, the rising part is connected to this pixel f1, and then this falling part, this q2, is connected to the pixel f0. Yeah, so this is our sum for the summation of the contributions of the two basis functions, and then we can simply plug in our definition. Here the falling slope, here the rising slope, this u, and that's it. Right here you can see this is our standard linear interpolation. And here it results from the convolution of the sampling points with a basis function. So we can see this general convolution of our pulse sequence with a basis function, in this case, results in linear interpolation. So linear interpolation is a special case of interpolations with basis functions. Yeah, so here's an example for it with numbers. We have two neighboring pixels. f0 is 10 and f1 should be 12. What is the sample right in the middle using linear interpolation? Answer, we can use this interpolation formula with u equals 0.5. So this is exactly the middle point then. So then we have f0 times 1 minus u plus u times f1. Plug in the numbers here and u equals 0.5. Then we get this formula here, 10 times 0.5 plus 0.5 times 12, and this is 11. Exactly what we expected. All right. Yeah, so observe the convolution here in space or time. What we just did here is a multiplication in the frequency domain, right? If you convolve in the time or space domain and go in the frequency domain, then this corresponds to a multiplication. Convolution turns into multiplication. And hence a convolution of two box functions, as we just did to obtain the triangular function, which have a sinc function in the frequency domain. These box functions in the frequency domain are sinc functions. That means the convolution of two box functions becomes a squared sinc function, a sinc function multiplied with itself in the frequency domain. So that means if we have small values in the sinc function, which corresponds to the stop band, then these small values become smaller after squaring. So that means we have a better filter in the frequency domain, and this better filter results in a better quality for our interpolated image. Right, and that's why in this case we indeed get better quality interpolation. So note this basis function is 0 for other integer x values where the other samples are, because that's where it starts and ends. And that means the interpolated curve goes through our samples. So that's nice. We obtain also the so-called C0 continuity, which is the continuity of the function itself. So there are no jumps anymore. But we have no C1 continuity, which is the continuity of the first derivative, which is we still get kinks, basically the sudden change in slope at each sample point. And still, this can still lead to artificial contours in images. So we would like to have also C1 continuity for better image quality. Yeah, so since this trick worked to obtain the C0 continuity, we apply the same trick again to obtain also the C1 continuity, and also turns out the C2 continuity, which is the continuity of the second derivative. So we take the triangle function and convolve it with itself, which in effect is 4 times convolution of the box function h1. Right, and this is what we call h4. And this results in the so-called cubic B-spline. Right, so h4, as it turns out, has 4 unit intervals, and so we have 4 different polynomials, and each polynomial is of third order. Yeah, so and that's why we can make the second derivative also continuous. So observe in the frequency domain, this B-spline is a sinc function to the 4th power, right? Sinc to the 4th power, where B is for basis. So this is our basis function for the convolution. And since now we have the sinc to the 4th power, that means we get even better stop-band attenuation, right? Because of the 4th power, that makes small values smaller and smaller, meaning we get better attenuation. So this now, since this now corresponds to 4 convolutions of our box function itself, the results extend over 4 unit intervals for our helper variable u, and hence we get 4 polynomials q. Each unit interval will have its own polynomial q1 to q4, as depicted in this plot. Where is this plot? Here's this plot. So here you can see it. We have those 4 unit intervals. The first goes from 0 to 1, the next goes from 1 to 2, then from 2 to 3, and then from 3 to 4. And this picture was made using this Python code here. And since we don't want to go to continuous space, I just subdivided each interval into 10 steps. Right, so this is an approximation. We have basically an accuracy of 1/10, and we set dt, this is the resolution, is 1/10. And then we can simply plot it using this Python code. So we use NumPy, matplotlib, scipy signal, and then we start with a box function, which here contains of 10 ones, right? And remember dt is 1/10, so this is 1 unit interval. Then we can compute h2 as a convolution of this box function with itself times dt, this is our time step or space step for images. And then same again, to obtain h4 we convolve h2 with itself and then we simply plot it, right? And this is the result. So I can simply copy and paste this code example, copy and open a terminal window, and simply start Python 3. So now we are in interactive mode, and now I can say paste, and then it executes it, and here it shows it, and here we go. So here we have our sync function, and you can see here this is not perfectly smooth because we just had dt equals 0.1. So we have an accuracy of 1/10 for this plot. Right. But it shows you qualitatively how this looks like. Yeah, so observe that in this way we get a very compact support in comparison with a sync function, which means our impulse response is quite short, still quite short, which means the length is only from 0 to 4, and it can be represented by polynomials qi of u of third order. Both make it quite efficient for an implementation, which is important for video coding purposes. Right. So the drawback is now that the B-spline does not go through 0 at the neighboring integer x values, at x values 1 and 3, or 10 and 30 in the above plot, such that an interpolation with a simple convolution will not go through the original sampling points or values, which is not good for image interpolation. Right. So going back here, so here is where you have your original sampling point, and here you have at 1 you have a neighboring pixel, and you can see here there's influence from the neighboring pixel to the pixel itself, which means it will not necessarily go through the original pixel values. So this is the drawback which we need to fix. Yeah, to fix this, we can pre-process the original signal or image first, such that the original samples are again obtained after the convolution with the B-splines, as you will see. So the trick here is to pre-process the image such that after interpolation we obtain our original sampling pixels back. So we don't perform the interpolation on the original image, but on the pre-processed image, also called compensated image. So it's a very simple trick or simple approach, which is actually working quite fine, as you will see coming up. So, but first we have to find the polynomials q1 to q4. Right? So far we just computed them numerically, but we have no representation as polynomials for arbitrary resolution. Remember, our computation was done on this grid of 1/10, right? And if we have polynomials, we have an arbitrary precision. So how do we get the polynomials? To obtain these polynomials, we start with a fourth derivative because it is easy to compute, and then we integrate 4 times to obtain the polynomial functions qi itself. Right, so we start with something simple. So it's again an engineering approach. If something seems to be too complicated, simplify it. So here the simplification is just going to the fourth derivative of our spline function. So we start with a convolution derivation rule. So when we have a convolution of 2 functions, h1, see this is our box functions, for instance, and we take the derivative, then this is the same as taking the derivative just of the first box function and then convolve it with the other one. And you can see that this is true by plugging in the definition of the convolution as this integral. So here we can see we have this integral over a of u times b of t minus u du, and taking the derivative, and Since this is a linear function, we can draw it inside the integral, and since there's only one of the two dependent on this derivative variable t, we apply just to this b. And that means when you look at this result here, this is a convolution of a of t with d to dt of b of t. Right? So we have just applied the derivative to the one of the two convolution functions. Yeah, and then we can extend it to 4 derivatives. We take the 4th derivative to our sequence of 4 convolutions of the box function itself. Right? Remember, H4 resulted as 4 times convolution of the box function itself. And if we apply this derivative rule 4 times, then each of the box function gets its own derivative, right, as you can see here. And then the derivative of a box function is really simple because it's mostly 0 except for the edges. At the beginning you have a positive Dirac because it's a rising slope. At the end you have a negative Dirac because it's a falling slope. Right, so this is what we get. So here in the beginning you have the positive Dirac, at the end of the box function you have this negative Dirac. Here, this negative Dirac. So this then results in what you can see here. I just simply took this result and convolved it 4 times with itself. Right, and this is then the result. You have those differently shifted Dirac functions. And if you have several of those same shifted Dirac functions, you add them up. So that's why you get those factors here. Right, and you obtain this result by again using this convolution property of Diracs. If you have a shifted Dirac and apply it with a function, then you have a shifted function. And if this other function again happens to be a shifted Dirac, then basically you combine those 2 shifts. Yeah, and you can also compute those coefficients in Python. You don't have to count them. So you simply represent the 2 Diracs from a unit from the box function as this array, plus 1, minus 1. So these are the factors of the 2 Dirac functions. And then you convolve them 4 times, basically. So here, convolution once. So you have the 2 derivative coefficients and you convolve them, then this is the result. And then you take this result and convolve it with itself again, and then this is the result. So here you can see now the new coefficients for the different shifts. Right? So here shift 0, shift 1, shift 2, shift 3, shift 4. So that corresponds to this equation here. Yeah, so here now you can see those 4 numbers. And again, you can just compute it by copy and paste. So copy, and going back to my Python window, ccdh, and here we get the result. Right. Yeah, so when we have the 3rd derivative, we simply obtain the when we have the 4th derivative, we obtain the 3rd derivative simply by integration, right? And we start without the integration constant. We add this integration constant later to obtain our continuities for the different derivatives. So first, simply enough, we have just the 3rd derivative, and for the 3rd derivative we have no continuity constraints. So here we also don't need an integration constant. So here, as a result, we get this piecewise constant function. So when we do the integration, we pass over the first Dirac. This gives us an area of 1, so it stays 1 until we hit the next Dirac. This next Dirac has the area of -4, so we add it to it. Then we end up at -3, ending down here. until we had the next hit the next Dirac at position 2, which has an area of +6. So we go from -3 to +3, stay there until we get to the Dirac at position 3, which has the area of -4. So we go from 3 to -1. And then finally the last Dirac has area 1 and we end up at 0 again. So this is our third derivative. And you can see it's indeed not continuous. It has jumps, right? But we accept it. Yeah, so this is our resulting function values. So we continue to integrate to obtain the polynomials q1 to q4. We start with q1, starting at the just obtained third derivative. Right, so here we have the first interval, third derivative has value 1. Right, now we need to integrate it. And what do we get when we integrate 1 with respect to u? Well, we get a u. So here we see it, third derivative was 1. Then we integrate it to obtain the second derivative, and we simply get the function u. Right, then we integrate again to obtain the first derivative. U integrated with respect to u is u squared over 2. Right, and then integration again. This integrated becomes u to the third power over 6. Right, and this is now the desired function, the desired polynomial for the first interval. So that was easy enough, right? Just 3 times integration and then we're done. Q2 follows next, but there it's not quite as easy because now we need to be careful with continuity at the point where the two intervals meet, right? Which is u equals 1 for Q1 and u equals 0 for Q2, which follows in the next interval. So at this point, the function value, the first derivative and the second derivative should be identical on both sides on the interval boundary. So we need to make sure that the second and first derivatives and the function itself are continuous across the interval boundary where Q1 and Q2 touch, and u equals 1 for the first interval and u equals 0 for the second interval, or mathematically second interval of Q1 for u equals 1 equals the second derivative of Q2 at u0. So here the second derivative should be identical for both sides. The first derivative should be identical for both sides, and the function value itself should be identical for both sides. Yeah, so we start again with the third derivative in the second interval. Now we have the third derivative having a function value of -3, and we don't need continuity here. So we can just go ahead and integrate. So for the second derivative, we now include an integration constant C2, which we choose such that it becomes continuous. Right? So here we have the second derivative, which we obtain by integrating the third derivative. So we have -3 times u plus our integration constant C2. Right? And for the continuity of the second derivative, we need that they have the same value on both sides of the boundary. So we know the second derivative of Q1 at u equals 1, which is 1. And we know the second derivative of Q2 at the point u0. So if you have u equals 0, then this disappeared, and we just keep C2. So we know 1 equals C2. So that's also easy enough. We have this integration constant, and this gives us our polynomial Q2, the second derivative of it. So now we can obtain the first derivative by integration and the integration constant C1. Right? This integrated gives us -3/2 times u squared plus u, so this becomes u, plus our c1. So again, comparing the values of the first derivative on both sides of our boundary gives us 1/2 is c1, right? 1/2 was the value on the first interval, c2 is the value on the second interval if we set u equals to 0. And that means we already have the first derivative of q2, which is this, right? We have this polynomial for the first derivative. So now we can integrate it again to get the final polynomial q2. Now with this integration constant c0. So again, we need to make sure that we have continuity now of the function values on both sides of the boundary. And we get 1/6 equals c2. Right? So this is the value from the first interval. And here this is the integration constant, which is left if we set u equals to 0. So now we have it. This is now our final polynomial q2, which gives us continuity for the function value, the first derivative, and the second derivative across this boundary between q1 and q2. So, nice. So, what's missing is just the upper two intervals, q3 and q2. And to make life simpler, we just simply mirror the lower polynomials by substituting u by 1 minus u. So we know that our B-spline is symmetric around the center, so we can simply mirror the two obtained polynomials to obtain q3 and q4. So that's easier, particularly if you do this using a symbolic mathematics package called WX maxima. So this allows us mathematical symbolic calculations. So this is what I did here. So Q3 is the mirrored version of Q2, which we obtain by substituting u by 1 minus u here. So this is what I did here. So here you can see this is basically Q3, but instead of u I put 1 minus u here. Right. So this is the result, and then I'm saying rational simplify as a command, and then it gives me this result. Right, and this gives me a simple polynomial. And we have coefficients of u to the 1, u to the 0, u to the second power, and u to the third power. And the same can be done for Q4. This is simply the mirrored version of Q1, substituting u by 1 minus u. So here you can see it. This was the first polynomial, and instead of u I have 1 minus u. Again, I'm doing rational simplify, and this is the polynomial I'm getting. So altogether we have 4 polynomials, one polynomial for each interval. So this is our result. So now we are basically done with our spline function. So this is now our spline function. It's a collection of 4 polynomials, one for each interval, right? Q1 to Q4. And that also means our convolution of our samples, which we call f of n. F of n are on the integer x values. And the convolution of these samples with the spline function h4 for the interpolation becomes now this sum here. Right? So this is our convolution sum. Here we have the sequence of our pixel values on the integer x grid. And then here is our spline polynomial. And observe that this n here is integer values, right? It goes only over the integer values on the x-axis. But this t here is float, right? And this allows us the interpolation. The t here can be 0.5, for instance, and then it gives us the middle value between 0 and, or the interpolated value between 0 and position 1. Right, so this is important for the interpolation. So now we can actually rewrite this h using our q's for the 4 values. Remember, what we actually have is those 4 q's. Right, so since the spline function here, h4, has its maximum at n equals 2, we shift it accordingly by +2 in the above formula so that it is centered around 0. So that's why we have this +2 here. So ideally we would like to have this peak of our spline function around 0, but we made this formulation such that it starts at 0, and that's why we need to have this shift to compensate for it. Now we can rewrite the continuous time variable t as the sum of an integer and not plus the float offset u on the unit interval. So here we have our t, and now we substitute our t by n naught, the nearest integer basically, plus u. And we choose this nearest integer such that the u is always positive. Yeah, so then we can reformulate it here in this way. So now instead of t, we have n naught plus u. Same here. And since we also know that our h4 has only limited length, starting at n naught, and then we can basically rewrite it here over the sum. So the n is not going over all possible n's, but only goes from n equals n naught minus 1. So this would be the beginning of the first interval, up to n naught plus 2. So that would be the end of the sinc function here, if we also have this u going from 0 to 1. So you can see it here. So this is basically going over the non-zero summends of this sum. That's why we can limit it here. And now we can do a very general interpolation. So we can take some pixel position and not say 1, and if you want to have the value at say position 1.2, then this u would be 0.2. Plug it in and we can see we have contributions from 4 intervals. So since we can write the spline function h4 as in equation 1 above with the 4 pieces, so now we can plug in the q's here, we can rewrite this sum as those 4 contributions from those 4 polynomials. So here, this sum here is rewritten using h4 as the 4 q's. Right. Since for each n we get a different q in h4. So that's why we have 4 contributions now. Or using this sum expression, here we have our function values within the range of our spline, and here we have our 4 polynomials of our spline. So here you can see this n goes down for our pixel index, and it also goes down here for our q index here. Yeah, so we see that we get the weighted sum of the 4 spline polynomials, each weighted by the corresponding sample value. So here you can see this f as the weighting of those polynomials. Here observe again that n naught and n are integer values, and u is the float helper variable in the range of 0 to 1 for the interpolated position, this fractional grid. Yeah, so here's an example. Take the sample points f of minus 1 equals 1, f of 0 equals 2, f of 1 equals 3, and f of 2 equals 4. We assume the other values are 0. This is shown in this picture here. So the blue are the original values. So we start here at minus 1, function value 1, then 2. So basically like a ramp, and then it goes back to 0 here. And here we have the integer x values, again discretized with 10 samples. So we have 1/10 accuracy. And Yeah, so this is an interval with u as position of the interpolation. So say here, maybe come close to 0.5. Yeah, so here the blue peaks are the original sample values. The green and red lines are the weighted and shifted B-spline functions. The long red line is the sum of them. So here you can see it. Here we have the corresponding spline functions. And you can see the sample values are actually much larger than the peaks of the corresponding spline functions. And that's because the peak of the spline functions is less than 1. It's 2/3 basically. So there's a big gap here. And also when you look at the neighboring contributions, here you can see they are not going through the zero, right? So that also means neighboring values can change the values here. And this is usually not wanted because we want to keep the original pixel values. But in any case, when you look at the sum of all those sinc functions, it comes quite close to the original pixel values, as you can see here. The red line here is the sum of all those spline functions. Goes up, 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 and then it goes down here. So it's actually indeed quite smooth, really smooth interpolation. But as you can see, it's not exactly going through the sample values, and particularly the last one here. There's actually a big gap here for the last one. So it goes along the original pixel values, but not through. Yeah. Right. So this is what we saw. So we want to interpolate a value at position u between 0 and 1 in the unit interval between sample points f0 and f1. We see that the sample points at both ends of this interval are connected to the peaks of the spline functions, the polynomials q3 and q4, so that they have the most influence on the interpolated value as expected. The two neighboring samples behind them still have some influence on the interpolated value, but only via the tails of the spline function q1 and q4, right, to both sides. Hence the considered to be interpolated interval has contributions from all four polynomials, which appear weighted in their sample values and add up as in this formula, which is equation 2 with n0 equals 0. So here we have this particular interval, and you can see here we get contributions from each interval according to the other sample values. Yeah, and this plot here, again, I made in Python using this script. Again, resolution 1/10. Here you can see I make the spline polynomial, again, by using 4 times convolutions. Then I'm taking our signal. Here you can see the signal contains the values from 1 to 5 on the integer x values, which means here it's on steps of 10, in between 0. And then we convolve it, this ramp function, with our obtained spline function using the red color. And here you can also see the individual contributions. So here you can see the individual contributions of the shifted and correspondingly weighted spline functions. And then basically the overall function corresponds to the summation of all those individual spline functions here. Yeah, so I can copy this. Copy, paste, and here you can see our plot. So here the individual spline functions, and here the overall spline function. Also observe they are slightly shifted here, and that comes from my discretization to 1/10. So it's more qualitatively. Yeah, we can see that our B-spline has the value of 1/6 at position 1 and 3. So these are the neighboring positions. Right. And it has the value of 4/6 or 2/3 at its center at sample position 2. Right, so this is here the center boundary, and you have 4/6 here in the center. Hence, the centered sample will be multiplied after convolution with a factor of 4/6, and that's why we saw it's correspondingly smaller than the actual value. And we also get the two neighboring samples with a factor of 1/6. So this is illustrated in this picture here. Here in the center, we have this value of 4/6 or 2/3. And here in the neighboring interval boundaries, we get 1/6. So basically, these are the contribution of the neighboring pixel values. So here we can also see if you have a constant sequence x of n equals k, and we can see what we get, then the interpolation on the integer grid values n are this. So we have 1/6 of the previous pixel, 4/6 of the center pixel, and 1/6 of the next pixel. Right, and if these are all the same, they're all k, we can factor it out, and you can see the sum is 1, right? 4/6 plus 2/6 is 6/6 is 1, so we get k. So in this case, it actually is fine, right? It goes right through the original sample values. But this is different for other examples. See, in our example, we had a sequence 1, 2, 3, 4, and then going down to 0. We had this picture, right? So here it's close, but not exactly. But mostly here, the last one, it really misses, right, when it goes down. So that's where we have the problem. So yeah, so this is basically the same as we just saw. And again, here we need this shift by 2 intervals in the last plot command because of the spline function, which has the maximum at t equals 2. So here you could see this concatenate zeros 20, which is 2 intervals, and this is because of again this offset, this shift by 2 for our spline function. Yeah, here we have again an interpolated grid of 1/10 of a pixel. We can also see that the interpolation does not go through the original pixel values, even though it is a nice and smooth interpolation, right? Has the nice smoothness properties. So how do we obtain a spline interpolation through the original pixels, which is desirable for images and videos? To see that, we first need to analyze what happens with the original pixels when we interpolate with a B-spline. So we stick on the integer grid and do the interpolation. Assume we already have a pre-processing of our original image, which produces the pixel values c of n, c for compensated, out of our image pixels x of n. So we just pretend that we have something, a compensated image, which produces our desired originals in the end, after applying the spline interpolation. The question is, how do we produce the c of n such that the original pixel values x of n are maintained after the spline interpolation? Right, so basically we work our way back. First we find a formulation which gives us the result after interpolation for the integer values on the integer grid, and then we go backwards to find how we obtain the c of n, the compensated image. Yeah, so this is basically this equation. We would like to have the following equality. So here you can see our pixels on the integer grid coming from our compensated image. And these factors now come from our spline interpolation, and they give us this new interpolated value, but on the pixel grid, on the integer pixel grid, right? And we want these x of n be the originals. So this x of n is our original pixel value, which we have already because it's on the integer grid. So we don't want to change it. We say the original pixel values are correct. We don't want to change them. But now we have a condition here. So this equation here shows us how to choose C to obtain X. And this looks underdetermined because we have 3 C values and just 1 X value. But this is not really the case, because this is this equation is true for each pixel X. So we have many of those equations, one for each pixel. But then of course we cannot really solve it in a closed form, and that's why the Z transform comes in handy, which is made to solve such problems. Yeah, so here the factor 1, 6 comes from the spline value at the neighboring positions 1 and 3, and the factor 4, 6 comes from the spline value at the center position 2. And C of n is our desired pre-processed or compensated image, pre-processing with some filtering operation. So here we just look at the integer pixel positions and observe that this condition has to hold for all integer values of n. So that's why we get many of those conditions. So how do we obtain C of n? We need to apply the Z transform as a tool because it is made for such recursive equations. Delays or advances can be formulated as multiplications with z to the minus 1 or with z respectively, which allows us to solve it for C of z in the z domain. So in the z domain we can factor out delays and advances to solve it. So the above equation in the z domain is this. So now x of z is the image in the z domain, and C of z is the compensated image in the z domain. And we can see C of n minus 1 becomes C of z times z to the minus 1, and C of n plus 1 becomes C of z times z, right? And that means we can simply factor it out, as we did here. So this can be rewritten as x of z equals C of z, and now we have all those factors, right? 1/6 z to the minus 1, 4/6, and then plus 1/6 times z. And this means we now have a formulation for C if we divide both sides by this factor here. Then we have C of z equals x of z divided by this polynomial. So indeed, in the z domain we obtained a nice closed formulation solution. And since we have a polynomial in the denominator, this looks like an IIR filter, right? If we have a denominator polynomial, this must be an IIR filter. And that means we can obtain C, the compensated image, from our original image by applying an IIR filter, right? So quite easy actually. The only problem is that this is also non-causal. So the Z is actually a non-causal part. So we need to find a solution for that. So we can rewrite the denominator polynomial of 1 as a product of two simpler polynomials using its roots, right? Sometimes also called zeros. So here you can see it. I factor out 1/6 and z, and then this is just a polynomial in z to the minus 1 with the factors 1, 4, and 1. And then we can apply the command roots in Octave or MATLAB or also Python. It's the same. And here we get those roots, right, as solutions. So that means we have our two roots z1 and z2. And it turns out that Z2 is simply 1 over Z1. So they have this simple relationship here. So we can simply rewrite it in this way. So here we now have a denominator which consists of a product of two polynomials of first order. Right. So that's easy enough. So here the pole Z2 would result in an instability because it's outside the unit circle. Right. So that's basically coming from the non-causal part that we discovered. Yeah, so we can rewrite our desired compensation filter C of Z as this. Right here we factor out this the -6 and this pole Z1, and then we have this simple expression here for our IIR filter. Here this IIR filter has two polynomials, and it has one causal and one anti-causal pole at Z1 equals -0.26. So here you can see it. Here's the anti-causal part, here's the causal part. And this is also how we solved the instability, because here the anti-causal pole is also stable. Right? Yeah, note that we have a non-causal part Z in our equation for C of n. How do we implement it? In images, we can actually solve this problem by separating a causal and an anti-causal filter, and then apply the anti-causal filter backwards over our image, backwards in time, which can be done because the image has no time direction. And this is shown in the following. First, the causal part is this, right, with a Z to the -1. And for that we filter along the causal direction from left to right or from up to down. And this generates an intermediate signal P of n with an IIR filter with a pole at Z1. So this is how this image shows how this structure looks like. So here we have the pixels coming in from left to right or top to bottom, and then we have this delay element. So this keeps the past sample, multiplies it with our factor Z1 and adds it to the output, to the input to obtain the output. So this is the result. This is our P of n, and that is the X of n coming in plus Z1 times P of n minus 1, so the last output. And when we take this and analyze it in the Z domain, this is what we get. So P of Z is X of Z plus Z1 times Z to the -1 times P of Z. Then we can again factor out P, get this, and then the result of the transfer function is this. So this is exactly the causal part of our IIR filter. Right? We see that it has indeed a pole at position Z equals Z1. This now represents 1/2 the causal part of our compensation filter. Then we apply the second part, which filters the intermediate signal P of n in the remaining anti-causal direction from right to left or from down to up. So this is now the trick. We reverse the direction. Right? So this is the reversal of direction. This is the anti-causal part. Right? We already saw this -6 Z1, which remained. And here is our anti-causal filter. And here the P is the output from the last filter. So here is now how we can implement it, this structure. So we have the output of the last filter multiplied with our constant here. And here we have now our feedback loop. And now this Z gives us the pixel to the right of this one, or to the top. So this is C of n plus 1. at the output, times this factor Z1. Right? So the output C of n is minus 6 Z1 times P, which comes in here, plus Z1 times C of n plus 1. It comes from this loop here. So then again in the Z domain for checking, this is the same here. And then we can factor out P, which we can see here. So basically we bring this C on the other side, then we have this vector, bring this over here and bring the P down. Then we have this as our result. And this is indeed our desired transfer function for the non-causal part. Right? So the total structure can be seen here in this diagram. We start with our image x, the pixel value is x of n. Let it go through this IIR filter, first order IIR filter here with this loop. Then have the constant here, multiply p of n with this constant. And then again we have this IIR filter now just going backwards, right, in the opposite direction. And this, as a result, gives us our C of n, the compensated image, to which we now can apply our spline interpolation. Yeah, and this is exactly what the Heinrich Hertz Institute proposal is for H.265. Right. So here's the formula again. We have this first part of our filter, the causal part, then here the second, the non-causal part. This gives us the compensated image, and this C of n is then used for the spline interpolation. So the resulting system is here. So starting on the left with the prediction residual, here we have some in-loop processing, here we have the output picture, here we have our IIR filter, which is doing the C of n computation, the compensated image. This then lands in the reference picture buffer, and this is output to the FIR filter, which is now doing the spline interpolation. And this is now used for motion compensation and prediction. Right here you can have precise fractional pixel motion vectors applied for motion compensation and prediction. So this gives you, this spline interpolation gives you more precision for this motion prediction and hence improved compression gain. Yeah, so the block IIR filter generates the C of n, and the FIR filter is the spline interpolator. In-loop processing is anti-blocking filtering and similar. So you can also read more about it in this paper here, Fractional Sample Motion Compensation using Generalized Interpolation. Not quite sure why this is blue. And this is from 2010 from the 28th Picture Coding Symposium, PCS 2010. Yeah, so here now back to our Python example. We take our example from above, where we saw that originally the interpolated curve was not going through the original samples. Now we apply our pre-processing to obtain C of n to see if we can fix it. Right. So same example as before, but now I'm taking more steps. So I'm taking actually 100th steps. So dt is now 100th to get more accuracy here. So the x is the same as this ramp function going back to 0 here. Then I plug it into my grid. So we have one sample, and then we have 99 zeros, next sample, and again 99 zeros, and so on, which is done here. So every 100th sample gets the x value. Here we compute or set the constants for our filter to obtain the compensated image. Here we have the Z1. Here we have the recursive part. Here we have the FIR part, which is just 1 for L filter. Here we have L filter of B, A. We filter X along axis 0, which means this should go down. It doesn't really matter because we have just one dimension anyway here. So this is the first axis, and in this case we just have one axis. In images we would have two axes, so we would apply this filter sequentially, horizontally and vertically. So now we make this was the causal filter part, right? So this produces P, and now we compute the non-causal part, and here you can see we do flipping. So we take the P and apply our L filter to the flipped P output, right? So this -1 means we flip the sequence. We start at the end and go back down to the beginning. So here the input is flipped. We get an output, and here we flip the output back, right? And here we apply this constant to obtain C. So C is then our pre-processed image or sequence in this case. And here you can also see how you apply the non-causal filtering. Basically, you can apply a causal filter like L filter and just flip the input sequence and flip the output sequence. Yeah, so then we can do the spline interpolation for this compensated image. So here I'm computing the spline, the B-spline, now with time steps of 1/100th or space steps of 1/100th. So here we have the total length, which should be close to 400. Then here we have our upsampled compensated image C. So here, let's see, C is our sequence, which came from the original X, right, the original pixel values. And for the interpolation, we need to create the intermediate sample points. So that's why we need to upsample this C by a factor of 100, because I want to have 99 samples in between for interpolation. So this would be a 100th pixel accuracy. Right, so here you have it. So every 100th pixel has the C, and we have zeros in between. So now we can do the interpolation using the spline, using L filter. So here you can see we have L filter. H4 is our spline, and since the spline is symmetric, it doesn't really matter in which direction we do the convolution. And here we have no IIR part, that's why we have a 1. And here this is the upsampled compensated signal. And then Xi is the interpolated signal, hopefully now going through the original sampling points. So now we plot the upsampled interpolated version, and plot it on top of the original XU, which is then red. And then we can take a look at it. So now I can copy and paste it. So copy, see if it works, copy and paste into our Python window. And indeed, so what we see here in red are the original sampling points, and the blue curve is now the interpolated curve of the compensated signal. So taking the compensated picture and applying spline interpolation now lets it go right through the original pixel values. So even here at the top, so remember the last one was really missing this last one because it was going down already. Here we have a nice fit, right? We have a really nice smooth curve, and it also goes through the original pixel points. So it actually works. So great, we have a nice tool now. Yeah, so here the explanation to it. As the signal, we again take a ramp function as in the previous example and its upsampled version. So here is the original ramp function. Here we do the upsampling now by this factor of 100. We compute then the signal from causal filtering, as we just saw, using L filter. and B, the FR part here is just 1. A, the IIR part contains this constant. And now we can do the anti-causal filtering by using flip LR at the input and output of our filter to reverse the filter direction. Right here you can see it. Here the input is flipped, P is flipped, and then with flip LR the output is flipped. We compute our B-spline basis function with 100 sampling points for each unit interval. So here we have finite interpolation now, 1/100th as a time or space step, and that's why we get a length of 397 for our spline function. The length is only 397 instead of 400 samples, and this shows that this is only a more or less unprecise approximation of the B-spline basis function, right, a numerical approximation. And for the reason of increasing accuracy, we went to 100 samples per unit interval instead of just 10 in the previous example. So now we can compute the interpolated curve from the upsampled compensated image C. Right. Compensated signal. So here we can see it. We have the upsampled version initialized with zeros, and then every 100th index gets the content of C assigned. Then we can apply our spline interpolation using L filter and H4 to the upsampled compensated image and obtain the spline interpolated original values back. So this is the curve that we just saw. So we can see that the interpolated curve blue indeed goes through the original samples in red at the full 100ths up to the accuracy of our approximated spline function. So that worked nicely, and we can see that it can be done. And in this way we indeed get much better interpolation for the fractional sample accuracy for our motion estimation and compensation. Okay, so that's it for today. Thank you for your attention and see you next time.